To test the sound here, see how it sounds.
When all the sky was buzzing and the ground was carpet green, and the weary children of the woods went dancing in between, and the people sang rejoicing when the fields were glad with grain, this song a celebration from their cities on the plain. This is my home, this is my only home, this is the only sacred ground I've ever known. Should I stray in the dark night lone, rock me goddess in the gentle arms of Eden. Now there's smoke across the harbor, and there's factories on the shore, and the world is ill with greed and will and enterprise and war. But I will lay my burdens in the cradle of your grace, on the shining beaches of your love and the sea of your embrace. This is my home, this is my only home, this is the only sacred ground that I've ever known. Should I stray in the dark night lone, rock me goddess in the gentle arms of Eden. Rock me goddess in the gentle arms of Eden. This is my only home, this is the only sacred ground that I've ever known. Should I stray in the dark night lone, rock me goddess in the gentle arms of Eden. Rock me goddess in the gentle arms of Eden.
So I lost a chicken yesterday, Joe Hawk. Still sitting on my fence with my wife yelling and screaming and running out there. Nice looking hawk, but now he knows I got chicken. I need a goat now. So there's all kinds of ways to get risk without math and physics. So I got a couple quotes, the favorite ones of mine there. Science gathers knowledge faster than society gathers wisdom. That's certainly true. You must always remember that there is much more stupidity than there is malice in the world. William Gaddis is a fairly famous author for you English guys. So today we're going to finish up talking about systemic accidents. And before we get started, I wanted to mention it's a systemic accident going on right now with the oil spill. The governor's blaming oil because oil's got a bad name right now, but it looks like the supply chain is what caused the spill. Went to all those ships that are across the thing, dragging their huge anchors across the bottom, and broke the spill, and then the automatic spill checker didn't work. So you can see how increased complexity is going to cause a chain of accidents, and we're not really sure who's at fault and how to blame it. And that's a characteristic of what we're going to talk about today, which is systemic accidents, because we're going to look at it from the point of view of airplanes. This is kind of a review, so you can figure out you're only one equation really that you have to know inside and out. Right up here on the board behind me, the lift equation, lift pressure over dynamic pressure is the lift coefficient, the plot with angle of attack. That's the heart of what we're doing, and it's the heart of what you'll be tested on at the midterm. And here's another little review of how this equation maps itself into practical life and death situations.
So why are pedostatics so important? This shows you the effect of density altitude, which is a crucial factor for most pilots, causing many accidents every year, especially at high altitude on hot days, high gross weights. So you can see here the takeoff distance increase for a normal airplane at 6,000 feet from sea level, more than doubling. And this can lead to a tragedy in a traffic pattern, because the pilot confuses a fast airspeed, which is his true airspeed, as he looks outside, relative to the indicated airspeed, which he should be paying attention to.
You're descending into a mountain valley, intending to land on a short runway, but you don't have much mountain flying experience. The field elevation is 6,000 feet, and the density altitude is 8,000 feet. It's windy and bumpy. Entering the downwind leg, you feel like you're going too fast, so you reduce power while holding altitude. Still, your ground speed seems high, and you inadvertently overshoot the turn from base to final. You feel like you're low, and you've heard that it's not smart to use steep bank angles in the traffic pattern. So you keep your turn shallow and use the left rudder to point the nose at the runway. Then, before you know it, the airplane shudders, stalls, and starts to spin. You're unable to recover.
So, you could see what happened was the perception of high ground speed caused the pilot to think he was going too fast, when he really should have been focusing on his indicated airspeed, which, if you remember, the test day indicated speed for stall is the same as the standard day, any day. So the pilot pulls back on the power, maintains back pressure on the stick, and does not focus on his low indicated airspeed. Then to make matters worse, as he's turning, he steps on the rudder instead of increasing the bank. And increasing the bank, of course, is a dangerous thing to do, but it looks dangerous, and that's why the pilots don't do it. They step on the rudder instead. Well, what this does is, of course, it tends to blank out the low wing and puts you in a departure situation for a stall. And actually, it's not a stall, it's a stall spin entry, which means that instead of a few hundred feet to recover, you need 500 to 1,000 feet to recover, which you normally don't have in the traffic pattern.
So that should make sense to everybody who's been following me. It's kind of a review of what's important. If it doesn't, then I urge you to come to office hours Thursday night at 6 and just nail it down. Yeah.
Could you go over just very quickly again the difference between the indicated airspeed and true airspeed?
The indicated airspeed is the equivalent airspeed. It's the airflow over the wings. It's the airflow, and we're going to cover that again in detail. The true airspeed is my airspeed through the air mass, So if I go up very high where it's very thin air, to get the same airflow I do at low altitude, I have to be going much faster. So the true airspeed is not normally displayed to the pilot, right? Except that as a computer to figure out how fast I'm going out, when will I get to my destination? But what's really important for flying is the indicated airspeed or the equivalent airspeed. We consider them the same in this class. And I'll cover that again this hour. We'll be covering that. So again, as a review, we've talked about the types of accidents. We talked about the Colgan. Let's see if I can get my annotation thing going, so I can use my favorite spotlight. So we talked about the Colgan aircraft as being a procedural aircraft where the pilot wants to kill you through his mistakes. Or the Boeing 737 MAX is an engineered accident where the design engineers or the engineers have designed an accident into the system. And then today we're going to talk about the ValuJet accident, which is a systemic accident. The procedures are so complicated or the automation is too big or one or the other. And again, the great example right now, if you want to just follow the Santa Barbara fuel spill, right? It looks like it's going to be a systemic accident. They won't know who's at fault, who's to blame, how it happened. It's going to be a really a mess trying to figure out what happened and how to fix that thing, that type of thing in the future. And then, of course, we talked about Air France. We talked about that accident where the pitot-static system went haywire. And it was probably a combination of procedural, engineered, and systemic causes. All three of those were in this Air France 449, the aircraft that went into the Atlantic Ocean from Rio de Janeiro flying to Paris. All boils down to attitude and evolution. It's time to adapt. So I get a great chance to talk to the younger generation because you're definitely, if we're going to have a future, it's your future, not mine. So we have to adapt or die out. This is just a summary again of what I'm kind of placing you what we did last class. We talked about the Colgan flight and all the problems with it. And today we're going to look at the DC-9 flight on a preventable aircraft with systemic. Another way to look at systemic accidents is it follows the inverse of Murphy's Law. We all know Murphy's Law, right? Something is go bad, it'll happen. Well, the inverse of Murphy's Law is, well, it hasn't happened, so I'll just cheat on this a little bit. It's going through a yellow light, right? Everybody's gone through a yellow light. So you go through a yellow light, nothing happened. Oh, so pretty soon you get in the habit of going through yellow lights. Right? Well, that's inverse of Murphy's Law. Someday someone's going to run the light going the other way, and everyone will end up with a chaotic accident, right? So when those kind of inverse Murphy Laws incidents pile up on you, if there's enough of them, they will cause a systemic accident. And if the system is complex enough, people will have workarounds for everything from signing off documents to doing what you do to pass classes. What I used to do when I was a college kid, you just, where am I going to spend my time? What am I doing this? What's my friend doing here? You got all these things balanced, and then you're taking your future in your hands with hoping that the balance that you pick is going to work out. So we're going to find out that not only were the pilots underpaid at ValuJet, but ValuJet did what the big airlines did to the ValuJet. They started hiring out contractors to shield themselves. So they hired people to do the maintenance, and they hired people to do the pencil whipping, and we weren't even sure who these people are that they hired. And the FAA didn't have enough inspectors, so they just downplayed the whole thing. So let's take a look at what happened at this in this accident. So it's about 5 minutes long. I cut it a little bit to make it a little bit shorter.
One hour to disaster.
1960.
A SaberTech driver
No.
pulls up at gate G2
1996.
at Miami International Airport with ValuJet cargo for flight 592. Inside the boxes are 144 out-of-date oxygen generators loosely packed. A ramp agent places them around a large airplane tire. The pilots are unaware that they have a dangerous load on board. 30 minutes to go. The loose packing and unsecured cargo jolt one of the generators into action. It begins to heat up. 11 minutes to disaster. The plane taxis to its takeoff position. In the hold, the surface of the metal generator gets hotter and hotter. Soon the heat ignites the cardboard box and bubble wrap, and the blaze begins. 10 minutes to disaster. Flight 592 takes off from Miami International by the oxygen produced by the generators. 3.5 minutes to go. The sound heard by the crew is one of the tires in the hold bursting, just as it did in the lab test. Fire begins to eat away at the systems on board. It is consuming everything in its path, including the control cables that run to the rear of the plane. Burns and begins to cave in.
So that airplane crashed in the Everglades, and she was the first female airline captain that's been killed. It was a horrible tragedy, and what made it worse was right here, the FAA didn't have enough inspectors, and the head of the FAA downplayed the accident, but the FAA eventually got blamed for it because it took 5 weeks to ground it. So it was kind of a deep irony that these systemic accidents, when you make the system more complex to reduce the accident, almost make another accident inevitable, even though it's less probable. And that's something that you're going to have to live with until we figure out a way to solve that problem. So here's what happened at the FAA. And this is going to lead right into ethics, which we'll talk about more detail next week, where you've got the good, the FAA is promoting good flying and aviation cost and convenience. That's good. That's a utilitarian principle that's used in society for ethics. But it's got to be balanced by rules and laws and regulations to keep the profit motive in check or in balance. So there has to be a balance between what's good and what's right. There has to be a balance, and checks and balances are normally what keep that going. And what happens is that financial priorities, if they're not in check, they can skew this balance that should exist between the good and the right and cause horrific problems, as we see here with the FAA, which didn't have enough people and often defended the airlines, as you'll see from this short clip on the FAA.
Relying on the FAA to ensure that all carriers fly safely has its limits. The FAA has less than 4,000 inspectors responsible for overseeing the safety of about 25,000 commercial flights in the U.S. every day. The crash of 3407 has raised anew questions about how well the FAA is doing its job. Questions that had previously surfaced in the mid-90s with the rapid rise of a low-cost airline called ValuJet. As ValuJet grew, so did its safety troubles, yet the FAA failed to heed warnings about repeated problems. Mary Schiavo was the Inspector General of the Department of Transportation at the time.
Instead of hitting them with violations, they were propping them up. My office said, whoa, wait a minute, this doesn't pass the smell test. When you've got an airline having this many problems, the FAA isn't doing proper oversight.
Hopes are fading now of finding any survivors from the crash of a ValuJet DC-9.
Then, in 1996, ValuJet Flight 592 from Miami caught fire and crashed into the Everglades.
Reportedly, the FAA says there were 109 people on board.
The Secretary of Transportation and the head of the FAA went into protective overdrive. The Secretary of Transportation flew down to Miami and stood in the Everglades, literally on the watery grave of 110 people, and said, ValuJet is a safe airline.
I want to emphasize that I have flown ValuJet. ValuJet is a safe airline, as is our entire aviation system.
I was very angry because they knew that that airline was troubled. Why? Because I'd been called into the Secretary of Transportation's office. The FAA administrator knew we were down there looking. We had presented some of our findings already.
Were they lying to the public?
I think so.
Why?
Because the FAA protects airlines.
The FAA's response to ValuJet exposed an inherent conflict in the agency's original mandate.
The Federal Aviation Act of 1958 gave the FAA two primary missions. One, safety. Two, promote aviation. In no particular order.
After the ValuJet crash, Congress, under public pressure, removed promotion from the FAA mandate. But a closer look at the legislation tells a different story.
There's a footnote in that legislation before Congress. And the footnote says, although we're changing the terminology from promote to encourage, we do not intend to change the way we do business. This is a change for the public consumption, and we're not changing how we work at the FAA. It was simply a sleight of hand.
Nick Sabatini worked inside the FAA for 30 years and was the head of aviation safety from 2001 through 2008.
I never did see that there was a conflict. I could easily compartmentalize. If I'm encouraging you to do better, I'm not encouraging you to necessarily grow your business in terms of promoting aviation. The promotion was promoting aviation safety, as we saw it.
Under Sabatini, the FAA forged a new regulatory approach with the industry called partnership programs. The FAA relied more on the airlines to self-report problems and help identify emerging safety risks.
We need to learn what those unknown risks are out there. Who is best positioned to know what risks they see every day? It's people who are operating the system and have their hands on the system every single day.
But critics say the FAA's collaborative approach went too far. A policy directive in 2003 called the Customer Service Initiative identified the airlines as the FAA's customers and encouraged the industry to challenge the decisions of FAA inspectors.
The problem, though, with the Customer Service Initiative, the way it was pushed, the way it was implemented, the way it was communicated to the workforce, it sent the wrong message. It sent a very bad message to the industry. It sent the message that, look, I can cut a deal. And all you had to do was make a phone call to, somebody that you became friends with over the years and request reconsideration, and it would be taken care of.
Both the FAA and industry say their success working together is borne out by statistics, that flying today is safer than ever. Prior to the crash of 3407, it had been 2.5 years since the last fatal commercial airline accident in the U.S.
In those intervening years, the United States air transportation system transported 2 billion people, maybe a little bit more. That is the equivalent of having transported the population of the United States more than 6 times without putting a scratch on anybody.
Okay, so I want to emphasize as an introduction, when we start talking about ethics, when we talk about the good, the utilitarian philosophy on the reason, he has just highlighted it. We got this huge number of people who are happy, so there's a few accidents. But there's a huge number of people, that's called the philosophy of the good, or utilitarianism, was started by Jeremy Bentham. It's one side of the balanced ethical equation.
But in the airline industry, there's a common expression that the absence of accidents doesn't necessarily mean you're safe.
When people say that, what do they mean? Well, what you really have to look at are the thousands of things that lead up to the accident in the first place. Human beings will make a lot of little mistakes that serve as a warning before a big mistake occurs and a big consequence. So what it means to really be safe is to be focused on those little warning signs and catching them early. It's only when we miss a bunch of those warning signs that we have a tragedy.
The question in the wake of 3407 is whether the FAA missed warning signs about safety problems at Colgan Air. As early as 1998, Colgan's problems were evident when the company began to grow as a regional airline. Colgan was supposed to upgrade its operations to meet the same level of safety as the major airlines. But in a letter from Colgan to the FAA obtained by Frontline, the company acknowledged it had to make significant improvements in order to meet the more stringent safety standards known as Part 121 regulations. The company committed to making substantial changes in pilot training, record-keeping, management, maintenance, and safety audit systems. The letter was signed by company founder Chuck Colgan. But 7 years later, in 2005, Colgan was still not meeting its regulatory requirements, says Chris Monteleone, who was a lead FAA inspector overseeing Colgan's growing operations.
There were not enough managers. There were not enough check airmen. There were not enough maintenance personnel.
Were they just overwhelmed?
They were acting as if they were overwhelmed. They couldn't control their business, the safety part of their business.
Monteleone says he took his concerns about Colgan to his office manager at the FAA, recommending enforcement actions against the company. But his manager, he says, was getting pushback from company president Mike Colgan.
Mike Colgan would call, or in some cases, it got to the point where he wrote about me to the office manager. And the office manager one time told my team, he said, Mike Colgan is a friend of this office. And that was the message. I mean, it was like, well, we already knew it, but he felt the need to reinforce it.
Did you, in the course of that, feel pressure not to stop that growth? In other words,
absolutely.
Were you seen as a roadblock?
Oh, absolutely.
The FAA office manager says he does not recall making those statements. But 3 years later, there were still problems when Colgan got another big contract from Continental. Colgan began flying a new airplane called the Q400, the type of plane that would crash in Buffalo. Did you get the sense that everybody was a bit overwhelmed by this airplane?
Yes, because there was a lot of growth. It was almost the same thing that was faced with the 2005 expansion, with this 2008 expansion of the Qs. There was a lot of growth. A lot of growing pains suffered by the company as well as the crews because it was new to all of us. None of us had ever operated this airplane before.
In February 2008, Colgan began flying passengers on the Q400. But the FAA was soon concerned that Colgan pilots were having trouble flying the airplane. There were reports that pilots were exercising poor judgment. And Colgan was short on check airmen, or supervisory pilots, for its Q400 fleet. So I guess were you a little surprised when they came to you and said, we want you to fly and supervise this crew?
Very surprised.
Why was that?
Because I'm not type rated in the aircraft. I'm not qualified in the aircraft. I had never flown the aircraft, and I didn't even know what the limitations of the aircraft were. Let alone it was very unclear as to exactly what we were supposed to be doing.
So did you have the sense they just wanted a warm body in that seat?
Yes.
There were other warnings about the safety culture at Colgan in 2008. In this NTSB file, we found a case that alarmed the FAA. It involved the actions of a Colgan captain on a flight out of New York City. The first officer on the flight was Ben Coates. It was Coates' job to calculate the weight limit on the flight, and his calculations showed the plane would be too heavy to fly. And you say to the captain, Captain, we're even more of a weight than we thought. What do you say?
Well, he said, well, why don't we just count 3 of those adults as children?
Really?
You know, just mark them down on the sheet as children, and that'll put us underweight. That's what he suggested.
Coates says he refused, and the captain took the weight manifest from him. Only after landing did Coates discover what had happened with the manifest. So when you looked at the paperwork, which had all the information on the weights and balances for the plane, what did you see?
Well, I saw it had been altered. My math had been altered. It had been changed so that our plane would no longer be overweight.
He made the limit higher
exactly.
So the plane would fit.
Yes.
And what you ended up with was a very heavy aircraft.
Yes, a very hard to fly, hard to climb at least airplane.
Unsafe, illegal airplane.
Yes.
Dangerous.
Yes.
Very dangerous, actually.
Very dangerous.
I don't understand why they would come in and support. I mean, it was breathtaking in its horror at the time. I mean, it was.
So she's the FAA inspector, and they fired the co-pilot who discovered the error, and they promoted the captain who altered and the FAA inspector couldn't get anything done out of it. There's a little final talk to this. Is you say, well, no, this was a long time ago. They fixed it, right? They fixed it. Well, the current president, current head of the FAA is a former Delta Airlines executive. So to talk about regulatory captain, his first action as head of the FAA was to fly the 737 MAX, the one that crashed twice. He flew that airplane and said, this airplane is totally safe. And he said that as the FAA administrator. I was so surprised by that I looked into his background and found out he was a former executive at Delta Airlines. So you keep thinking that you've solved this problem. Then they get in the airplane, oh, they had the accidents, but they fixed it. But then the system keeps going, it keeps going. And all you hear pretty much from the politicians these days is there's too much regulation, right? Well, there is a lot of silly regulation. There's no sense we want to get rid of it. But a lot of regulation is necessary for the balance between the utilitarian philosophy and the practical philosophy of making things work and making them safe. So that kind of sums up the accidents. And we're going to do today now for the rest of this hour and next hour is I'm going to take you into the cockpit and show you what the pilot sees, because he has a simulated environment. We talked about living in the simulation in the last class, but we all live in our own simulated environment. We all have sensors. We're only dealing with our sensors, and our brain takes that and creates a virtual world for ourselves to live in. And that's just how things are. When I say our brain, so where are we? If our brain is making these decisions, I'm talking about our brain, and where exactly am I? Well, the self, pretty sure from neuroscientists, is a creation. It's a creation of the subconscious in cahoots with our culture that was given to us. The two of those things create what we call the self. So we can talk about my brain and my sensors as if there's something apart from me, but they're really not. They're really integral. So the pilot, when he goes into he has the same thing. He has a simulated environment in front of him, and how does he manage to make things work? Well, what I got shown in red in here is what I want you to remember. Make sure you know these red things. Avionics is electronics, guidance, navigation, and control. Right? Are the three things that the pilot gets in his simulated environment in the cockpit. Guidance is situational awareness. Every pilot would know what you're talking about when you say situational awareness. I know where I am, and I know what I'm doing, and the same for the airplane. Navigation in GNC, navigation is PVT. PVT is position, velocity, and time. Each one of these letters has their own simulation, We'll go into that in a little bit of detail later this hour. And C is control. Control is pretty much with avionics. It's like fly-by-wire. It's how do you define an aircraft? Am I moving something physically when I move the airplane? When I pull back on the stick, what's happening back here? All kinds of things like that are now changing with avionics, and that has to be understood. So what I've got shown in red here is what you should remember as far as the buzzwords. And this is what the pilot sees in the cockpit. When he sees guidance, situational awareness, he sees the attitude indicator, which is shown over here on the left. This is shown in a right bank. That little W there is the landing gear, so that's the airplane, and that's the horizon. And then this the numbers showing whether he's pitching up or whether he's pitching down. Below the attitude indicator is the horizontal situation indicator. It shows him his magnetic heading. So he is heading magnetically north, which is not necessarily true north. We have to look, but it's magnetic north because the aircraft has a sensor on the wing. The aircraft, this is my granddaughter's airplane. Out here on the wing is a little magnetic compass sensor, and it's sending the magnetic heading into the cockpit. That's what he's looking at on the horizontal situation indicator. Now, the true course is related to something comes from the ground. It tells him where he is relative to a course that's laid out on the ground. And then this is always a test question. I said, what happens if the airplane is going straight up, or what if it's going straight down? What's its heading? And the heading is undefined. There is no heading if he's going straight up or straight down. So what happens to this this HSI and this attitude indicator. They tend to either go dark, or they'll spin. They'll spin. In the old days, when I was learning how to fly, there would be gyros, and the gyros would tumble. They would actually tumble, and you'd have to reset them. So heading is undefined, as is roll angle when you're going straight up or straight down. This is the test question. I'm pretty sure I'll ask it again for your class. So the cockpit displays ADI heading indicator, or the two HSI horizontal situation indicator. That's what a pilot uses to land his airplane. Pretty much these two instruments, while making sure that he has adequate airflow over the wing. And I always ask a test question: what's the difference between the magnetic heading and the true course? So I will cover that this hour or early next hour. Make sure you understand today the difference between magnetic heading and true course. Those of you who are hikers, you will be your Boy Scouts, you'll know exactly what I'm talking about ahead of time. And the other thing we have to look at is, does the pilot know how high his airplane is? We live in this bubble called the atmosphere. When the airplanes fly in this bubble, how do they keep separated from each other? How do they know how high as the atmosphere changes from day to day? As it rains, it gets hot, it gets cold, the atmosphere changes. If I'm using sensors that sense that, how do I use that data in the cockpit? That we'll cover today also. So here's the attitude indicator. That's what the pilot sees. We're going to focus on this guy right here, the attitude indicator. Whether it's small or a big airplane, they look the same. And I'm going to show you a little bit how it works. Just a 1-minute video that's pretty quick. What would you see in the cockpit?
So as I bank into a turn to the left, I'm going to set it at about 15 degrees.
Notice in the left bank how the sky pointer, the thick white index, moves to the right when you are in the left bank. This can be confusing, but when you turn to the left, the sky pointer, that thick line, will point to the right. Here's another picture of what it looks like from a climbing right turn, but the sky pointer has been removed now.
Okay, I think I have a, let's see, a picture of this. So you can use my HSI picture. This is from an Airbus. That's from an Airbus. That's what it looks like in a left turn. That's what it looks like in a left turn. That was a sky pointer. That some simulations that are written don't get that correctly and can be confusing. That's what I was saying, when it can be confusing. But you've got that video for you to look at. Let's talk about the airspeed again. I had the question about why is the airspeed important? The airspeed's over here on the left, and that's the inside of the airspeed indicator. I'm showing you here what it looks like. The airspeed indicator measures the airflow over the wing, and it's calibrated so that it would be at sea level. Otherwise I'd have two variables in here. So they make this one, and the airspeed indicator, they change this to sea level. That's a constant. And then when they do that, they can make this equivalent airspeed. So you're only looking at the equivalent airspeed, which is what you want, because that's what tells you when you're going to stall. That's how the airspeed indicator, and then there's the formula for Q. You can see there's only one formula you really need to know. You need to know this guy inside and out, and what each of those things mean in a practical sense. In a practical sense. That's what I'll be asking you about. And of course, if you hear the word indicated airspeed or equivalent airspeed in this class, they're the same thing. The only difference is between equivalent and true airspeed. The airspeed is the ram pressure minus the static pressure. If the pitot tube gets blocked, we saw that over here. If the pitot tube gets blocked, then the airspeed indicator becomes an altimeter. All it runs is static pressure. There's no more ram pressure. So when you climb, if you're climbing, your airspeed indicator is going to increase, even if you're slowing down. Does that make sense? It makes sense. This is an altimeter now. It's just going to go up. So you can lead to some really crazy things, decision making in the cockpit when that happens. And we think that's what caused the Air France accident that killed everybody in that flight from Rio de Janeiro to Paris. So if the airplane is climbing and the pitot system is blocked, all you've got is the static port. So as the airplane climbs, the static pressure decreases, the ram air pressure is locked, so it will increase the airspeed indicator. So the airspeed indicator will increase even though the airplane is climbing and slowing down. It can stall, showing an increasing airspeed. Until it starts descending, you are going to show an increasing airspeed. And this is possibly or probably what caused the crash of Flight 447. Okay, and possibly not turning on the fetal heat, so they froze up in a storm. So this is the atmosphere that's programmed into your altimeter. I've got an altimeter I'm showing you here. I've just unwound it. I've taken the circle and I've unwound it. All the altimeter is a barometric measuring device that's calibrated with the mathematical standard atmosphere. And where does the mathematical standard atmosphere come? Oh, equations way beyond this class, right? Very complicated equations from the ICAO, International Standards, develop this set of equations. So what we've done is our altimeter is built to represent all these numbers in one gauge, but it doesn't know what the reference point is. When we fly, we don't know what the reference is. Normally we take 2992 for a standard day at sea level, but we don't know what particular the atmospheric pressure is today. We'd have to call somebody and get that information from the airport tower, for example. But here's a rule of thumb that's kind of cool. If you look at your height, indicated height in a standard atmosphere versus the mercury setting, 2992. And remember what that is. The mercury setting is if this is the sea level here, if that's sea level, and I put my finger on the straw, then I could raise that mercury level up. If this was full of mercury, and it would go up 2992 inches on a standard day. That's how it was developed, and we've kept that through the years. Every 1,000 feet, look at this, 2992 at 0 feet MSL. Let's go to 1,000 feet mean sea level MSL. 2985. Let's go to 2,000 feet, 2782. So it looks like 1 inch of atmospheric pressure is 1,000 feet, and that's a really good rule of thumb. If you go up 1,000 feet, your altimeter is going to unwind 1 inch, which is 1 rotation of the large dial. That's what it looks like. So this large dial here, this large one that's pointed at the 6, this altimeter is reading 630 feet MSL right now. That inside one is the 10,000 foot marker. That will move over here to 1 when you have them above 10,000 feet. So it's kind of like a repeating clock. And it's going to measure what your reference relative to whatever you dial in here. That's called the Colesman window. Whatever dialed into the Colesman window that's where I'm going to set this pressure device. I'm going to set it here. So if this is sea level, I see sea level pressure is 3012, then my altimeter, I'm going to want to line it up like that. I'm going to want to line it up. If I don't line it up, then I'll be indicating the wrong altitude for the atmosphere that I'm in. Okay. So let's take a look at this. I put together a little video that shows you how this works.
An aircraft altimeter is calibrated to carry a standard mathematical atmosphere. That atmosphere changes 1,000 foot for every measured inch of mercury decrease from some reference that's dialed in to the window of the altimeter. An aircraft altimeter measures barometric atmospheric pressure relative to a selected reference for 0 feet at 0 feet MSL. The selected reference is entered as inches of mercury, 2992 for a standard mathematical atmosphere. The atmosphere is calibrated to indicate plus 1,000 feet for every inch of mercury decrease in measured pressure below.
So let's suppose this ruler is an altimeter, a barometric altimeter. And what a barometric altimeter does, like this ruler, is it carries a calibrated atmosphere, a mathematical atmosphere in it. And that atmosphere is calibrated such that at 0 feet to sea level, I will measure 29.92 inches of mercury. In other words, that's the height that a mercury will rise if you had a mercury tube at 0 feet in the standard atmosphere. So if the pressure is standard in this mathematical atmosphere, 2992, the altimeter would read 0 feet. If, however, the altimeter reads 2892, 1 inch less, 1 inch is about 1,000 feet of increase of altitude. So as the inches decrease, if the altimeter measures 2892, it will read 1,000 feet. The big hand will make one, just like a clock, it'll make one big circle and read 1,000 feet. If, on the other hand, it feels 1 inch bigger than 2992, then it will decrease 1,000 feet from its reference of 0 feet. So here it's reading 0 feet at 2992 in the mathematical standard atmosphere. The question is the atmosphere mathematically, is the atmosphere that we're in a mathematical atmosphere? So I went out to Morro Bay and I got some water. It's a little dirty out there, but it's still, I think it's still drinkable. Anyway, what I saw is that at sea level, you can see at sea level, the pressure was 2892. So it's a low pressure day. That normally means the weather's going to be bad. Normally low pressure is associated with bad. So if I took my altimeter out there to Morro Bay and left it assigned at 2992, if I left this as the reference, then the altimeter would go to 2992, and at Morro Bay, which is at sea level, right? That's where the sea level is. It would measure 2892, but because the reference is set at 2992, it would indicate 1,000 feet. So say I was flying. What if I was flying in the clouds and I said, oh gee, I need to descend and see where the base of the clouds are. Maybe the base of the clouds are 500 feet. So I put the airplane in a descent because I'm indicating 1,000 feet on my altimeter, and I put it in a descent. What would happen? Well, I just went right into the drink. Oh my goodness. I don't know if I could find myself. I fell in there somewhere. Okay, so pilots remember this by saying, if I'm flying from high pressure to low pressure, from high to low, look out below. Because you might think that you're going to clear the mountaintop. You might think you have 1,000 feet above that mountaintop or sea level. But when you decrease that clearance to what you think is still positive 0, you're going to fly into the ground. High to low, look out below. So what happens? Well, again, if I were to look at this and say, oh man, that isn't that good. So suppose I went back out there and that was sea level now. This is sea level day. Now it's a little different. And now I leave my thing at 2992, and I can see if this is actually sea level, then when I read 2892, I will be 1,000 feet. I will be 1,000 feet above the sea. But what happens if it's a high pressure day? If it's a high pressure day, this, the pressure at sea level is going to be 3012. Suppose the pressure is 3012 on a high pressure day, and I leave 2992 set up. I think, and I leave 2992, I think, at sea level. Well, now when I read 3012, I'll think that the altimeter will be reading 1,000 feet below sea level. So if it's a high pressure day, I'll read, and I read 3012, and I think that is, if I have 2992 dialed in, but the pressure is actually 3012, the altimeter will read low by 1,000 feet. Now it's telling me I'm too low, so I would want to go up and get rid of that 1,000 feet and come up to at least here. So when I'm at 0 and go up to here, when I read 2992, I will actually be 1,000 feet above sea level. So I will be actually higher than my altimeter reads. So from low to high, enjoy the sky. So this is when you fly into high pressure, which is good weather, then you'll be higher than you think you are with the altimeter reading set. Of course, the best thing is to have the altimeter set correctly. If you set it, no matter where you are, if you set it correctly at the right value for sea level, then your standard mathematical atmosphere, which is calibrated in the altimeter, will tend to match the actual atmosphere that you're flying in. Okay, hope that helps. Good luck. Anyone is any good? Not bad. Not bad. So I have one more thing. My granddaughter saw me do that video, She had to get involved.
Okay, this is a demonstration of air pressure using mercury. That's mercury. Okay, so show how mercury works if you.
So this is actually called a mouse, Grandpa.
Oh, okay.
It's just we're using it instead of mercury. So if we want to have it, it would be like 30 inches if it was mercury.
29.92 exactly, but almost 30. That's very good.
Yeah.
Yeah, it was right. Now you're gonna drink that mercury?
Yeah.
You don't drink real mercury.
Yeah, don't drink real mercury.
Okay.
Yeah, so do pilots, before they take off, do they calibrate the altimeter to match?
In a way, they call the tower, and they're at the tower, and they say, what's the pressure in San Luis Obispo today? And they'll say, pressure today is 2974. And the pilot will dial in 2974, and then he should read the height of the airport where he's sitting at that time, which is 212 feet. So when you get the altimeter settings, dial in 2974, and I should read 212 feet, then I know that it'll read 0 at sea level on that day. But I am flying, everyone is flying the mathematical atmosphere, right? So, I mean, because the atmosphere, the actual atmosphere, whatever temperature it wants to be, whatever pressure it wants to be. But if we're flying separated mathematically in our mathematical atmosphere, we keep everybody separated. But that's how the pilot does it. Now, when you get up at 18,000 feet above any mountains, when you're not worried about hitting the ground, if you're not worried about it, 2992. Everybody puts 2992 in, and then they separate themselves with flight levels, 1,000-foot flight levels up above 18,000 feet. But below that, you should get the closest altimeter setting to whoever's reporting it accurately, whatever weather station or whatever tower you call them. If you don't, you take the danger of flying into a mountain or a hill, or flying into someone else in bad weather. Good question. Any other? Okay, let's take 10 minutes, okay? I'll see you back in 10 minutes.
So tell me about your airplane.
So basically, I'm making this for my school's cardboard challenge. Basically, it's like a cardboard thing. I blended that myself, and I blended that myself. I just made that USA sign for nothing. And then I wrote my name right there. And then U.S. Army F5600. I just wrote that.
It's a 5600.
Oh.
Okay, 5600.
And I just colored it randomly. Basically, my dad helped me. I used them in my grandma's sewing bins.
It looks a lot like the T-38 white one, doesn't it?
Yeah, basically. It's for my cardboard challenge.
I know.
But no one really wins anything.
Do you think it
and
might?
Then here's the stand.
Oh, okay. How does that work?
So basically, basically the thing, you can either go like, I'll just put it right here, like that, or like that.
Oh, that's very cool. Yeah.
Here's some blending montage. And that's all.
Thank you for showing that to me. Thanks.
So she let me have it one more day. I guess her dad's gonna take it to his work. So I got it one more day on the cardboard challenge at her school. She's 7. So the video you saw with of the drinking was 6. It was last year. This one I just made last week. So let's just review a little bit. Don't forget, the pilot's looking at this altimeter gauge in the cockpit. Let me get my trusty spotlight going here. This is the altimeter here. Yeah. And every time the large hand goes around once, that's 1 inch of mercury relative to whatever he's got set in what's called the Colesman window. And you're flying, if I unwound the altimeter, it would be like a stick. It's a standard mathematical atmosphere. Very complicated equations derive this, but once it's derived, that's what everybody flies that is in an airplane that buys an altimeter, everyone. Now, notice it's not GPS. I'm not flying GPS altitude. I'm flying a standard atmosphere model that existed before GPS. That's an important thing to remember. So the pilot selects the altitude reference with the Colesman knob. He turns this little knob and it changes the number that's in the little window there. And that reference comes from weather reports. It displays thousands of feet with the big hand, or with the little hand, and then hundreds of feet with the big hand, and then 20. Looks like each 100 is divided up into 20-foot increments. So you can pretty much figure out about within 10 feet where you're at. So if you're in a standard atmosphere, then 2992 is set in here. If you're not in the standard atmosphere, then you have to put the closest correct value that's reported by a weather agency or the tower. And that's how you keep separated and stay above the ground. So if I was on the ground right now, I would be at an elevation of 540 feet, 535 feet above the ground. And that'd be how high that ground location would be above sea level. Above 18,000 feet, I think I mentioned this, all aircraft set 2992 in because you don't have to worry about hitting the ground above 18,000 feet. So everybody separates from themselves by having the same thing dialed in when you're at very high altitudes. And they're called flight levels. To determine the height of an aircraft above the ground, the pilot must subtract this height shown from the height that he knows above the ground. So if I was at the ground level of 530 feet and I read 530 feet, I know I'd be 0 feet above the ground. I'd be at the ground level. And the pilot has to do that subtraction in his head while flying all the time. All the time. So what happens about temperature? What if I'm not what if my atmosphere is cold? It's getting cold in winter. Well, the atmosphere condenses. You see, in a hot day and then on a cold day, how the atmosphere condenses. So the same reading of 4,000 feet will occur at a lower altitude on a cold day because the atmosphere is compressed. Does that make sense? Okay, so if that's a test question, yeah, go ahead.
Just repeat that again.
So if it's a cold day, the atmosphere gets compressed. So if I'm at 4,000 feet indicated and it's hot out when I take off, and then I fly and I stay at 4,000 feet, but the weather gets cold, I will actually, my altimeter will actually decrease, right? If I stay at 4,000 feet, I'll be lowered to the ground because the atmosphere gets compressed. That's how temperature affects it. We don't care when we're flying because it happens to everybody flying, right? It happens to everybody. But if you're trying to clear a mountain on a cold day, right? Winter flying over the mountains could be hazardous if you're using your altimeter. These are standard day numbers. I will not ask you to remember them. If I asked you for it, this right here, you can just copy them off. One thing we haven't covered though is where's sea level? Where's that? Doesn't the tide go up and down? Where exactly? Who sets sea level? We're going to talk about that now. That's kind of a difficult concept. Where is sea level? Is GPS sea level the same as other people's sea level? Well, this is where it's going to get a little complicated. Aircraft heights are measured from mean sea level, and mean sea level is determined from what's called the geoid. What the hell is a geoid? So I brought one to show you. This is the geoid right here. It's kind of lumpy. And what it is where water would go if it were free to flow. If water were free to flow, where would it go? You know, if it didn't hit the shorelines. And it would look kind of lumpy like that because of how mass is distributed. Grand Canyon's over here, mountains are over here. So the water would be up here and down here. But what would be say the same would be my plumb bob. Wherever I drop the plumb bob or wherever I built a house, carpenters know everything I'm talking about here. Wherever I wanted to measure normal, I am perpendicular to what's called the geoid. I'm perpendicular to it, right? So it may not be perpendicular to the surface. It may not be the Leaning Tower of Pisa might actually be along the lines of the geoid. It's not, but it could be. So the idea of how we translate all this stuff into maps is important. And this young man did a pretty good job of making that work. Let's see if I can get this thing running.
I'm gonna have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat.
And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer.
Model of the so-called geoid. To understand this geoid, we need a bit of imagination.
If the planet would be covered completely by water, the gravity field inside, or the gravity field of Earth, would...
Okay, so let me stop it right here and talk a little bit, because the young man said there's no right answer. And from his point of view, that's correct. There definitely are right answers in this class for how you look at it. So this is a whole set of maps that determine the navigation positioning. And we use the green dotted line right here. That's called number two. That green dotted line is the GPS altitude. That comes from the GPS altitude. I got old GPS here. The GPS actually looks like an ellipsoid. It's kind of bigger around the middle, kind of like an older man. And it's called the WGS84. That's just the name they give it, the WGS84. But it's a ellipsoid. And when you get the GPS coordinates of a point, you're getting the coordinates of a point that lie on a smooth mathematical surface that looks like number two, right? But look at number one. Number one is the ocean. That's the actual ocean. And the ocean goes up and down. High tides, low tides, big high tides, low tides. Depends on where the moon is. So the ocean goes up, 10, 15, 20 feet. So the ocean does not determine MSL. What determines MSL is called the geoid. And the geoid is number 5. It's number 5. And remember, I just said a few slides ago, I said, if you drop a plumb bob, you're going to be perpendicular to the geoid. You'll drop the perpendicular. So you can see these are plumb bobs that are dropped. Number 3 are plumb bobs, and they're all perpendicular to the geoid. And what the geoid is take the moon away, get rid of the moon, right? And then get rid of, let the water flow as it would. The earth is rotating, but the water is flowing. Let it flow out, and it'll end up with an irregular looking surface because of the mass distribution around it. But the gravity is going to be the same at every point on that surface. It's going to be the same. At sea level, it's going to be 32.17 feet per second squared, or 9.8 meters per second squared. Every point on here is going to have that same value of gravity if you measured it with an accelerometer. And if you measured its angle, the perpendicular to the geoid will be straight up. Why is that so important? Because the second most used navigation system, it's on all our weapon systems, is inertial navigation. Inertial navigation navigates with respect to the geoid because they take a platform and they may use accelerometers and they say, okay, find level. And it does this, and it says right here, okay, let's navigate, let's go navigate. And it uses accelerometers and gyros to position itself and tell you very accurately where you are. It does that relative to the geoid. So if say you're attacking a system somewhere and you shoot a missile at it, but the bad guys jam your missile, they jam the GPS. Well, then you transition to the inertial navigation system. Nobody can jam an INS. It's self-contained. Nobody knows you even have it on. So all of our weapon systems and many of our military aircraft have inertial navigation systems as a backup to the GPS. So that's what the geoid is. I wanted to take a little bit of time and show you, the Earth itself, as it spins, these are satellites up here. As the Earth spins, it looks like an ellipsoid. And when we look at it on a map, we have to make sure that we're converting correctly from GPS to our map coordinates, because number 4 here is the height, and we want to make sure we don't end up flying through a mountain because we didn't have the right conversion in place.
Shapes the sea surface like that. If we had no land masses, nothing, the sea surface would look like the geoid.
This model is widely used by all kinds of scientists. It's been calculated previously, but never with the precision that we can see now. This global sea level reference will be used worldwide as the zero level of heights. This is very important for GPS navigation and major engineering projects. So the scientific world has been...
This kind of just shows you a review of it. Here's the land mass, and the height above the geoid, which is MSL, that capital H is mean sea level. That's height above the sea level. You have to take into account the geoid difference between it and the ground, and then the little h, which is the ellipsoid. So the ellipsoid is a circle going like this. The geoid has this relationship to the ellipsoid, and then there is this relationship with the MSL that's in the cockpit. See how complicated it gets to figure out where you're at, right? And do you have to know how to do all that? Well, if you don't do it right, in Grenada, our F-16s bombed a hospital. They thought it was a barracks. The GPS coordinates for the barracks were the actual coordinates of a hospital because they did not make the conversion from GPS coordinates to map coordinates. Right? You have to make that conversion. If you buy a Garmin receiver, a GPS receiver, and you're a hiker, it'll ask you what map you're using. And you enter that map, and then the GPS Garmin receiver will make that conversion for you. If you use this in the mountains, you're on your own, right? You're on your own. So you could be up to 2 miles off hiking in the mountains with your cell phone. And it's happened. Doctors have called helicopters because they're running out of battery and they're 2 miles from where they thought they were. They didn't know where they were because the GPS wasn't working on their phone. It's working fine. It's giving them GPS coordinates, but he's got a map that he didn't convert to map coordinates. So if you ever go hiking in the boondocks, backpacking, make sure you get a GPS receiver and don't use your phone for that. It talked about all this. So the geoid backup systems for GPS, that's important to know. Remember, it's inertial navigation. Inertial navigation systems are backup navigation systems for the GPS. If the GPS goes down, doesn't work, you can use an inertial navigation system. From minutes 8, I guess I could try this. I got 2 minutes where I talk about the geoid from a previous class. I thought I did a good job. Let's see if I did or not. Oops. It's not gonna let me go there. Nope, it's not. Okay. So you'll have to go there on your own and just look at minutes 8:30 to 10:30. I try to explain what I just said to me a little bit better from a previous class. This is from week 9. Again, the red numbers is all I expect you to know right now. Make sure you understand what those red numbers are. There's something new here at the bottom where I talk about time sources. You've got 2 time sources. You've got time that comes from GPS, the GPS time that we all use. That's the time that's using here. That's the time that comes off your phone. That's GPS time. Then there's a time that the labs compute. The labs compute called universal time, Zulu time. It's called Zulu time, and that comes from laboratories all over the world. And they kind of tie GPS time to that universal time. I'm not going to ask you for anything on this view graph. We'll talk more about this on week 9. So none of this is testable except make the red letters. The red letters, you should know what they mean. We've been talking about them all day. Oh, all right. So let's go and make that conversion. Let's look at that conversion. Here's the heading indicator, what I call the HSI down here. There's the heading indicator, and the true course on the runway. Let's go to San Luis Obispo runway. Here's the runway at true course. That's 303 degrees. So if I go to San Luis Obispo Airport here, and I align with the runway on this map, if I measure it, it'll measure 303 degrees. But the runway says it's runway 29. It's runway 29. Why is that? There's a 13-degree difference between what's indicated over here on the heading indicator and the actual true course that I'd measure on the map. It's important that you take that into account if you're traveling somewhere, right? So how do you do that? So this is a pilot map. It's called a sectional. And over here, I don't know if you can see it. Over here, there's a line that's coming in, a little dashed line over here, and it's got the number 13 on it. 13 on it. That line that comes very close to San Luis Obispo, Morro Bay, tells me that if I want to get the magnetic heading from the true course, 13 degrees east, 13 degrees east, subtract 13 degrees. Subtract 13 degrees. And that magnetic heading is actually changing as the magnetic pole changes. But let's see, for practical purposes, what I want you to remember is the pilot looks at magnetic heading, not true course. The true course is a map thing that has to be done offline with flight planning. And your runway heading, if I line up with this red arrow, if I line up with that, my heading will read 290. It'll read 29. I'll be heading 290. Okay. That takes care of our 2 primary instruments, the attitude indicator and the HSI, the heading indicator. Now the thing is, magnetic north is moving all. It's moving. That 13 degrees is going to change. So when that 13 degrees becomes 18 degrees, they'll have to change the runway heading. They'll have to make this runway 28. They'll have to make it runway 28 because the magnetic pole is moving. This is kind of cool. This is the magnetic pole over here. Look at how it's moved. It's moved a huge amount. There's the north. There's the real North Pole. The real North Pole. You know, the Earth is spinning about the North Pole, right? So there's a North Pole, and that never changed. That defines true course. That's what you measure on your map with the latitude line. You measure that true course. But this magnetic pole is moving all over the place, and that's what's published over here. You can see here it's 14 degrees east. So whenever I'm flying in this area, the difference between the magnetic pole and the true pole is 14 degrees. I have to subtract 14 degrees from the true course to get the magnetic course. If it's west, then you'd have to add it. If it's west. Why is it changing? Because every 12 million years, they think it flips. The magnetic pole flips. And they say we're due for one. They say we're due for a flip. So it's certainly not going to be in our lifetime, mine or yours, but that's what the scientists tell us. So let's kind of look at these are the avionics that are taken over now, the stuff that we put on our airplanes. Look how tiny it is. It's actually smaller than that now. It's all electronic. It's like a big, huge video game. And you can see in the center, there's the attitude indicator and the HSI is underneath it. And then there's your God's eye moving map of where you are. It's like a map like this set up in front of you so you can see exactly where you are. It does all the conversions that you need. There's a civil cockpit. This is called a multifunction display. It's got a moving map that moves as you fly over it. It's also called a heads-up display. Heads-up display would actually display on the window panels, would display some of this information while you're looking out the window. The gear wheel stays the same. Here's the gear wheel right there. It looks like a little little wheel. All airplanes keep the wheel. There's a flap over here. So your gear and flaps always changes the same. But it's not uncommon to hear a pilot of this kind of system say, ask his co-pilot, what's it doing? The co-pilot, I don't know, but it's doing it again. Gee, what could go wrong with this system? So as we automate, remember, what would he say about systemic accidents? As you automate, the accident rate goes down, but the accident is going to be guaranteed. And it's going to be hard to figure out exactly what happened. And pilots are used to this. So I call this the good, the bad, and the ugly. And I've got little demos for each one. This one is the good. This is the good.
Friends would walk up to me and just be like, what the f is in your mug? And I would just tell them, that's.
The aircraft is an A330, built by aerospace giant Airbus. Though there are 700 in service, there hadn't been a single passenger fatality until Flight 447. This history of reliability rests on a highly computerized flight control system.
They're highly automated. They're some of the leading edge technology in aviation even today.
Powerful computer systems are designed to control everything from airspeed and altitude to turning the aircraft. The design philosophy that automation improves safety.
You know why the annotations are coming on.
In a flight simulator,
V1, rotate.
veteran pilot Martin Alder demonstrates the features of these computer systems.
Gear up. In a conventional airplane, instead of this side stick, I'd have quite a big control column here, but you need plenty of leverage to apply the mechanical forces you need to move the control surfaces to control the airplane.
In a conventional airplane, the pilot pulls mechanical levers to operate a hydraulic control system. But on the A330, this heavyweight gear is replaced by an electronic system called fly-by-wire. The pilot tells the flight computer what he wants to do, but it is the computer that translates this intention into action and executes the maneuver.
So if I want to go to the left, stick to the left. Round to the left.
The flight computer adjusts the control surfaces and the aircraft turns left. Maneuvers like this cause the A330 to lose altitude. So the advanced computer compensates by increasing power and pitching the nose up to provide the right amount of lift. The pilot does nothing.
I take my hands off, and there we are. It's flying round. Vertical speed 0, 25 degrees of bank, 240 knots. It's going to fly around at 25 degrees of bank, keep doing this until we get bored.
The flight computer won't carry out any pilot command that endangers the safety of the aircraft.
If the pilot were to lose control for some reason, the system would save the airplane.
Right. Yeah. Of course, they made that before the.
Looking for a light.
They made that before the 554 crash, the 330 that crashed into the Atlantic Ocean. Right. So it will kill you if you don't know what you're doing. And the side stick, of course, as you heard Captain Sully Sullenberger talk about, the side stick in his mind was one of the worst things because they weren't hooked up together. The guy on the left didn't know what the guy on the right was doing because the side sticks don't talk to each other. But in reality, if you look back on it, it was the pitot system froze up, and it can cause a lot of confusion and warnings in the cockpit that confused everybody, especially the new guy. So you can see, again, and I wanted to emphasize, that was partially a systemic accident. Why? Because if we didn't find that airplane and go through that cockpit communication, we have no idea what brought it down. There's a Malaysian airplane out there somewhere, Right now, they have no idea what brought it down. There's all kind of theories that are out there, but you can see how hard it is to figure out when you have the data. It's still hard to figure out what made it. But that was as good. That was as good as it gets. And you heard the Airbus philosophy there, at least before they had the major crashes. Here's the bad. This is the bad that you get.
About this stuff. So that was the good. So let's look at the bad. If we look at the bad, we have to look at almost all military aircraft. So this is pretty much all military aircraft. This is the F-22. And you might remember the F-22. That was Mark Morgenfeld, the guy that flew the Lockheed entry for the F-35.
So that was Morgenfeld. And that's pretty much what happens to all military airplanes. And the ugly kind of tells you why. This is good. We're going to look at the Swedish airplane, Gripen. I was involved a little bit with this. There's a company called Calspan that fixes this problem when the military aircraft is trying to become operational. But this one is the Gripen, brand new airplane, one of its first test flights. Of course, the pilot got out of that, so he said, but this is, unfortunately, this is kind of typical for the development of a new airplane, and it's called the pilot-induced oscillation. And what happens is kind of tricky. When you've got a computer, you add all kind of time delays into the system. Time delays, this bus has to talk to that bus, and it happens so fast that the engineers say the pilot will never see it. Well, that's true. If that was the only one thing that he or she is looking at, they would never see it. Unfortunately, these delays add up. The more computers you add to the system, the more time delay there is. And it doesn't help that you got a 64-bit system. It still happens. So when the time delay builds up, the pilot is going to pull back on the stick to do something. He'll pull back, and there's a little delay. And he doesn't feel it right away. They don't feel it, so he pulls back harder. And by the time it kicks in, he's got the harder, and he goes up too hard. Oh, so you get in this pilot-induced oscillation out of phase. What makes it crash? That's not what makes it crash. Is all you're going to do is let go of it, and you'll be fine. But what happens is the hydraulic pressure, if you move the stick too much, like Tom Morgenfeld on that F-22, the F-22 has nozzles in the back. They're nozzles, and the nozzles move also. So he had the gear coming up on a go-around. He's moving the nozzles, and he's moving the stick, and the hydraulic pressure does what? Goes to zero. When it goes to zero, the airplane becomes, it's unstable. It's an unstable airplane. That's how they build them, so that they're highly maneuverable. So you got this unstable airplane that's going to do crazy things. He's out of phase with it. By the time the hydraulic pressure builds back up again, he's got, who knows what control he's got into, and he actually crashed that airplane. He lived through it, so unfortunately, he was okay. But that is typical of what happens. So we'll see that happen in the space shuttle. The space shuttle happened the same thing, and we see it here with the Gripen. And again, there's this company called Calspan out of Buffalo, New York, and I almost went to work for them instead of coming here when I left the Air Force. They're very good company, and they fix this kind of problem. They fix these kind of problems. But let's take a look at automation and then see how it really panned out. This is how I would summarize the history of automation. This is how it all started. That's an Airbus, I think.
Aircraft manufacturers have tried to fix that problem by designing the pilot out of the cockpit. This is the first fully automated plane, flown by a computer.
Fortunately, everybody got out of that airplane. There were observers on the plane. They all got out. So you got to be, it's a dangerous world. Now, the good news is the accident rate is going down. So it's getting, because you're eliminating the pilot, who's usually the main probabilistically speaking, statistically speaking, the pilot is the source of the most accidents. So as you eliminate the pilot, your accidents are going down. But the accidents that you generate become inevitable. The complexity of the system, the automation makes an accident inevitable, and you don't know who to hold responsible. When the Prius gas pedal went forward and killed a highway patrolman in California and his whole family, who got held responsible for that? Nobody. NASA spent a year looking at the code that Toyota put into that Prius, and they couldn't find anything wrong with it. It was so complicated, came from so many different sources, 5,000 lines of code. They had no idea where it came from, even what language it was written in. So the accidents, and who you hold accountable for? If you watch that movie Worth, where they rewarded the 9/11, that's what's going to happen probably in the future. If you have a certain accident, a certain one of your families get killed, there'll be a formula, an algorithm, as Facebook would say, that gives you a certain payout, because it won't be worth going farther than that. The legal fees would swamp anything else because there's no way to find out who really was responsible, who wrote it, who was in charge of it. So as we automate, pull people out of it, you have to realize you're taking responsibility out of the system, and you're distributing that responsibility over decades of time and thousands of people who were involved in the development. And that's what we talk about inverse Murphy law. This is kind of interesting. This is Sheryl Crow. I don't know Sheryl Crow. I'm sure you know her more than I do. But this is funny because she was stuck in their Tesla. The screen went black. And Elon Musk called, I guess you could call people in your Tesla. If you had a problem, you could call somebody else. So, and she called, and Elon Musk answered her and showed her how to fix it. Okay, so let's review now. This is good. So let's we're moving along. One thing I would suggest now, you got three tries for your quiz. You're not going to get more than 2 hours for the test, and the test is going to be 20 matchings and five numerical answers. You might try, like, give yourself a 2-hour limit. See if you can do the quiz in 2 hours. To see if you can. I hate to make you feel bad, but when I used to teach in-person classes, these quizzes were due at the end of class. So like now, you'd have to turn this quiz in before you left today, right? I mean, that's how it used to be. So the thing is, when you have infinite time, you'll fill space with infinite time. So see if you can put a time limit on yourself. And then if you don't get it or it didn't come out right, then get with your group, you know, or come see the third. So you have, because your third quiz, it's going to stop on you. And I'm trying to get you used to having only just one shot at the quiz. Here's some technical help for this quiz. Let's see. I don't remember what I did here. Let's see if I remember this.
For example, let's assume the altimeter setting at San Francisco is 30.25, and at Santa Barbara the altimeter setting is 29.25. At 1,000 feet MSL above San Francisco, the pressure is 29.25. This is the same as the sea level pressure at Santa Barbara. Do you see how the 29.25 pressure level gradually sloped from 1,000 feet MSL over San Francisco down to sea level at Santa Barbara? It can be said that pressure levels drop when flying towards an area of lower pressure. Can you see what's happening? The level where the pressure is 27.25 inches of mercury actually slopes downward closer to the surface, yet the altimeter is still reading 3,000 feet. If we don't continue to update the altimeter setting, the indicated altitude, what's shown on the altimeter's face, becomes different from our true altitude, or actual height above sea level. Over Santa Barbara, our indicated altitude is 3,000 feet, but our true altitude is only 2,000 feet above sea level. Is this a problem? Yes. What happens if there is a mountain at 2,500 feet along your path? Looking at the face of the altimeter, it appears you'll clear the mountain by 500 feet. In reality, you're 500 feet below the top of the mountain. Under these conditions, there's a good chance that your aeroplane's landing gear might conk the head of some camper sitting around a campfire on top of that hill. What a shock it would be if it were nighttime and you thought you would clear that 2,500-foot mountain by 500 feet. you might end up with a Coleman stove, camping gear, and raccoons stuck to your aeroplane. For example, let's assume...
That's an example of how pilots learn about what I just told you today. And I'm kind of more interested in realizing that you see how we use simulation. We use mathematical models for everything, whether it's your cell phone, whatever. We use models so often that it's like the atmosphere. We just don't feel it anymore. We don't feel the atmospheric pressure. We don't think that we're using models, but we do. We do for just about everything. Here are some questions. Again, if you want to study for the exam is going to be very much like the questions that are on the quiz. The difference is that what you want to do when you look at your quiz questions is see what topic that quiz question is covering. Because I'm not going to ask you the same question, right? The answer won't be the same, but it'll cover the same topic. So if I ask you a question about altimeters and high to low and low to high, then make sure you understand how that works, how the system works, how do you fly. If you have an incorrect altimeter setting and you're flying into low pressure, your actual altitude is decreasing. It's actually decreasing. And I think yeah, this is a numerical number. How was the standard atmosphere carried by the altimeter aligned with the actual atmosphere while flying? Remember that? That's where you dial in the Colesman setting. You dial in the correct altimeter setting for the area you're in using the Colesman. That's how you would answer that one. Explain the significance of the common pilot mantra when flying from high to low, look out below. Well, if I have the incorrectly high altimeter set here, incorrectly high altimeter setting, then the actual altitude will be significantly below what my altimeter is indicating on the standard atmosphere. And this is a repeat of the diagram. You got this as a PDF file. Where is 0 feet? So I might just give you this picture and say, circle what is 0 feet. And of course, you know, the 0 feet is the geoid. That's number 5. The geoid is where gravity is the same. The magnitude of gravity is 32.17 feet per second squared, or 9.8 meters per second. So that's the magnitude of it. That defines where the surface is. And then the surface is always such that if you drop a plumb bob, to that surface, you always get a 90 degrees. So that's how you build a house. You build a house, a big skyscraper. They use the geoid for building skyscrapers. And inertial navigation systems, the essential backup to GPS for military systems are inertial navigation systems. Circle the number at right that defines 0 feet. Okay, we just did that. That would be number 5. At the far right, the pilot put 2992 in, but the correct setting is 2986. Explain the consequences of setting the altimeter 1.5 inches too high. Well, you know, 1.56 inches is 1,560 feet, right? So your altimeter will read 1,560 feet too high. You'll be 1,560 feet below what's indicated on your altimeter. Hey, if you follow this, I think you're ready. This you might want to put this view graph aside when you're studying for your test. Make sure you got it all. Yeah, go ahead. No, I will be here in class. So if you want me to be available while you're taking the test, you want to come in class. You can take the test anytime that day, right? It's open everything except no friends, right? It's just it's your own. It's by yourself. But yeah, you can use any access, anything you would like. I used to say no electronics. There's no way to do that today with COVID. It's impossible. So I just no use whatever you want. Like I said, this is so if this is the quiz for this time, but if this was the test, this would be filled out on the left. This would go to 20. This would go to 20, and they'd be worth half a point apiece. Each one would be worth half a point. So that'd be 10 points total. And I might add 5 or 6 over here just to throw you off with the goofy answers on the right-hand side. So you'd see like 20 matches, each worth a half a point. And then you'll have 5 questions like this, very similar to this. What number must be set in the Colesman window? I should know that one, right? 2992, right? If you're flying in the standard atmosphere above 18,000 feet, everybody puts 2992. let's look at the next one. We got time. The FAA says San Luis Obispo is 212 feet. And we know what that means. If I dial in the correct altimeter setting at San Luis Obispo, my altimeter will read 212 feet. What defines the reference level for that is 200 feet above what? Let's take a look at this. 200 feet, 0 feet MSL is the actual surface height of the ocean at Morro Bay at midnight, as this is the mathematical base of the standard atmosphere. That wrong answer is wrong as hell, right? Because the tide goes up and down, you know, the ocean goes up and down. I used to play handball with a fisherman, and he just bought a GPS, and he'd see me in the handball court, and he'd say, my GPS reads I'm 30 feet below the water. What good is this GPS? Well, that's where the GPS altitude is. The tides go up and down, you know. Again, you can't use GPS altitude as relative to the ground unless you make a conversion. And with the ocean, it's impossible. 0 feet is measured from an imaginary surface 212 feet directly below the control tower, like with a tape line. So if I measure the tape line down 212 feet, that would be, and that's wrong. Right? That is not right. That is not measured. 0 feet MSL has nothing to do with real altitude. It comes from the geoid, the geoid only. 0 feet MSL is the mathematically defined surface over the Earth called a geoid near the slow airport, where the magnitude of gravity is 32.17405, add 5 more decimal places, feet per second squared. That is correct. That's how you define the geoid. So it's a meaningless number. It's meaningless. It's as meaningless as 2992 is. But what it does is it sets a reference so that if everybody's using that number, we're all using it, we can stay away from each other, and then we can convert to a map, and we can navigate. It's used for conversion. But again, for my purposes, what I'd like you to realize is how mathematically oriented everything is. All we've done for the last 3 weeks, we're a third done with this class now. We're a third done with it. All we've done is talk about this equation. How airplanes fly, what equivalent airspeed is, how accidents happen. It's all related to that equation. And to things like where zero height is. This next one looks like that's too hard for me. I'm gonna let you work on that one. Magnetic variation is 15 degrees east. This means the variation between magnetic north and true north varies between plus and minus 15 degrees. That's wrong, because the east tells you which way it varies. It's not. The slow airport runway named 29 has a true course of 29 minus 15. That's wrong. The conversion is applied incorrectly in that a magnetic compass operating near San Luis Obispo will have a 15 degrees error toward the east. A magnetic compass will have an error of 15 degrees toward the east. Is that right? I'm not sure that's right or not. I have to think about that. The direction pointing to the magnetic North Pole is 15 degrees to the left of the direction pointing to the Earth's North Pole. I'm not sure about that either. It's too hard. You're going to have to work that one. Okay. All right. I think you're going to be fine. Again, all this stuff on avionics, make sure you understand the red stuff. The red things there are important. And you guys have a great weekend. Thursday night, 6 o'clock. Have any questions? I'll be Zooming 6 o'clock. Other than that, have a great weekend. Bye. You bet.
Thank you.
Welcome. Thank you. Yeah, thanks. You too.